again. This is tech blog number 8, another video blog. This week I'm going to be focusing on sorting algorithms. So it's kind of a different tack than what we've done so far in our work at DBC, since we've been mostly focused on just finding a way, like any way, to make something work. Choosing the right algorithm is all about finding the best way to make something work. So different speeds, or maybe there's different uses of memory, and different ones will fit different situations and be right for different situations or different tasks. So it turns out that there are a ton of different ways to ask the computer to sort an array, and some of them are significantly more efficient than others. They mostly have names based on the approach they take, like insertion sort, bubble sort, heap sort, and partition exchange sort, which is fast enough and popular enough that it's actually just called quick sort most of the time. So we're going to be demoing the different methods in Ruby, and hopefully we'll be able to see the differences in efficiency with these methods. Sorting methods usually rely on recursion, but we'll try not to get too bogged down with that here. So if you're interested in recursion, you should check out Darwin's blog on it from this week, which I will put a link to in the description. It's pretty concise and it's not tough to follow. So thanks for that, Darwin. So how can we get started with sorting? How would we sort a list by hand if we had no computer? My first thought was manually sorting like a deck of cards. So I pick up 2 cards and I put them in order. Easy. After that, I pick up 1 card at a time and see where it goes on the list. Front, back, or somewhere in the middle. Then I have 3 cards and go on from there, front, back, or somewhere between these 3. This is called insertion sorting. You insert 1 card each time at its proper place. It's pretty easy because a deck of cards isn't that big, and also because we can guess where to look along the row of cards in our hand. The computer, by contrast, cannot guess like that. It has to look at each card in its hand in order every time it adds a new card. So it has to start from the back and go 1, 2, 3, and check against every single number. This is what it looks like when you have insertion sorting done by the computer. It starts with this jumbled mess and then looks at 6, okay, and 5. 5 needs to go behind 6. And it inserts it at the proper place. Then looks at 3 and inserts it at the proper place in this array. And so it goes on like that. Obviously, it's pretty slow, and we can see how it would get even slower the bigger the numbers get, the bigger the total length of the array gets. Searching through thousands of numbers thousands of times is tough, even for a computer. So how can we sort faster? We have to find a way to reduce the number of checks it takes to order each number. So instead of checking every number against the whole list, we need to break the list up into smaller pieces until we can do just 1 comparison at a time, and then put it all back together. This is where recursion comes in. Let's see if I can find it here. Yeah, this is a graphical representation of quicksort, which is also called partition exchange sorting. So it picks a value. This is with colors, by the way, if you couldn't tell. It's sorting the colors in order, according to Rogi Biv, I guess. It takes the first value, or any random value will work, and decides with every other color, is it higher or lower, left or right? So red goes on the left side of this greeny guy, and blues go on the right side. And then it does the same thing again with this new smaller array, splits into 2 parts based on higher or lower than the random selection point, and does it again and again and again, 1 higher and 1 lower, until we have 1 higher and 1 lower, just 1. And then look at these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are all in order. So it goes all the way down, breaks them up into ones, and then puts them back together in order, and we come up with this. All the way down and then back up the chain. This isn't the fastest implementation of quicksort, but it's the easiest one to visualize, I think. So eventually we wind up with single values, all split in order, and we just put them back together, going back up the chain. This is how recursion works. We split something up, down, 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 until we get to the base case, the one that's easiest to handle. Then we return one level up and use the base case answer to complete that level. Then we use that answer to complete the next level. And we move all the way back up the chain like this until we return to our original function. So now we're going to take this to the lab and test both insertion method and quicksort with a real array. So let's do that now. This array has over 5,000 entries, as you can see. And down here, this is quicksort as it's implemented in JavaScript. It's the easiest one for me to write and kind of the easiest one, I think. It's the same one that I just presented to you in the color split. So it creates a left array and a right array and makes the pivot point the first number in the array and splits everything into the left or the right array based on whether it's less than or greater than the pivot point. And then it calls itself on the left array and on the right array. So it goes down, down, down until each array is just one entry. And then it goes back up and concatenates each mini array. Each miniature array gets concatenated back up, including the pivot, all the way back up to the main original function, where these get concatenated, and then that's our answer that gets returned. And then down here is the insertion method. We're not going to bother going through every single one of these in the code because they're a little bit tedious, and merge sort is still actually a little bit hard for me to understand. Anyway, so I've got multiple sort methods. We've got insertion and quicksort, and I've got them called down here with a little timer check to see how long each one takes. Merge sort, bubble sort, and native sort for Ruby's quicksort are commented out right now. We're just going to look at this in the insertion sort and the quicksort that we just looked at and see how long it takes each of them to sort these 5,000 plus values. So let's look here and see what we get. It takes a while. And we can see here there's 5,685 entries. And quicksort takes a little under 7/10 of a second. An insertion method takes just over a whole second. And we can see that it gets even faster, actually, the larger the numbers get. Going back here, we can look at, this is a graph of quicksort, merge sort, heap sort, and insertion sort. And this is the number of data points along the bottom and the amount of time it takes to solve along on the left side here. So red is quicksort. You can see that it's the fastest. After a while, it develops this pattern. It's the fastest. It takes the most values in the least amount of time. For 20 values, or whatever it is, this may just be a placeholder number. But for the same number of values, merge sort takes more time, heap sort takes more time, and insertion sort takes even more time. And here is the time taken for an even larger number of entries. So we can see that quicksort and merge sort are pretty close to each other. They're both pretty fast for way, way tons of entries. Heap sort is a little bit slower, and insertion sort just keeps getting worse and worse. The more numbers you add, the slower it is. It gets slower way faster than insertion or than quicksort does. So there are many other sorting algorithms as well. Merge sort splits everything into pairs and then orders those pairs. So it splits this 8-number array into pairs, and then it orders those pairs like this, and then it rebuilds pairs of 4, and then 8, and so on, pulling all those in order, first from each pair, and then from each set of 4. So we'll see here in a minute, it's going to compose a sorted array of 4 by pulling from the first element, sorting each from the first, and then 3, and then 5, and then 6, and then it'll create another array of 4 over here that's sorted. By pulling from the first and judging each on the first in the array. 1, 2. Okay. It's almost as fast as quicksort in most cases, as we saw on this graph here. Bubble sort is probably my favorite, just because it's so terrible. It goes along the entire array and compares each item to its neighbor one at a time and transposes them if they're out of order. And then it starts all the way over at the beginning and does the same thing again. See, 5 and 3 are still out of order here after it's gone through them. It's going to have to go through again and again and again in order to get them all sorted. And it only stops once it goes through the entire array once and sees no more changes are necessary. So it goes through this a ridiculous number of times just to sort these 8 numbers. It's silly. So we can now uncomment the calls for merge sort, bubble sort, and Ruby's native sort. Well, actually, let's leave that one for now. So if we call quicksort, insertion, merge, and bubble, what do we get? So we see that quicksort, again, is the fastest. Insertion is slower. Merge is even slower than this quicksort because it's not the proper quicksort. It's just an easier one to understand. And then, of course, bubble sort takes almost 5 seconds just by itself, when the rest of them took less than 2 seconds combined, or just about 2 seconds combined. So that's pretty pitiful on bubble sort's part. And here we can look at Ruby's native quicksort. So this is quicksort that Ruby does when you just tell it to sort. If you say .sort, this is what Ruby will do. And it's quite quick. Yeah. So here it's way, way faster than any of these other methods. It's like, thousandths, 10,000ths of a second that it takes. And there's 2 reasons I think that it's so much faster. One reason is that it's actually a better implementation, a faster version of what we did up here. And it's also built into the language, so it's not being written out by us by hand. Having it built into the language, I think, saves it time as well. And it's impossible, or it's been very difficult so far for other programmers to improve on Ruby's native sorting method within Ruby. Building a better sort in Ruby has proven very, very difficult to do. So those are a few of the sorting methods. There's a whole bunch more, actually. But those are a few of the ones that are most commonly discussed and commonly used. Bubble sort, I think, is probably not used that often. But insertion sort, merge sort, quick sort, which is also, as I said, called partition exchange sort, are used for different purposes. Quicksort is the most common one. It's the one that's standard in JavaScript and the one that's standard in Ruby. because it's usually the fastest for most use cases. Obviously, I haven't typed out a whole bunch of code for this session. I had it pre-written up here. And it's because I didn't write these algorithms. I just took them from resources that I found. And I figured this already might be a little bit long of a video without me typing everything out and making syntax errors like I usually do. So hopefully, even though I haven't typed these out and explained them line by line, it's been a kind of illustrative exercise to look at the different sorting methods and the elapsed time that they take for a given array length. I think it's really interesting, even if I couldn't write all of these myself necessarily, and I have a hard time visualizing some of them and getting my head around them. But they're fun to mess with, and coming up with a new sorting algorithm is always exciting. I think in the UK, the guy who came up with Quicksort got knighted. So he's like Sir, Quicksort now, or whatever it is. So that's just a little bit of a peek into algorithms and what I've been able to find out about sorting algorithms so far. So I hope you guys have enjoyed it as much as I have, and I'll talk to you next time.